Okay, so I know the theme of this program is cosmology, but I'm going to talk about something a little bit closer to home today, which is the dark matter in our own galaxy. So similar to what Carlos talked about, although like much closer to the Galactic Center. And what exactly I mean by much closer will become clear in just a minute. So what do we know from observations about the dark matter in the Milky Way? This is kind of a compilation from a couple of years ago. The red points here are all the kinematic tracers in our galaxy, so things we're measuring the rotational velocity of. And so you've got the rotational velocities as a function of radius. We live out here at about 8 kiloparsecs. And you can see there's a lot of scatter. Outside of the solar circle, it's pretty clear that, that it's flat-ish. What's supposed to be a gray band here is like a bracketing of all of the baryonic models. So there's something like 70 different baryonic models for distributions of baryons that go into that. So if it were just baryons, you would predict to lie in this gray band. And obviously outside of the circle, there's some disagreement. Actually, what this paper showed was inside of the circle, there's some disagreement as well. And so there is evidence for dark matter within the solar circle. The region that I'm going to be talking about today is actually basically just along this axis. So we're looking at the sub-parsec regime, which is really, really, really close to the galactic center. And I'm going to be talking about what we know and don't know about the dark matter that lives there. Okay, so that's from observations. From simulations, we know a little bit of stuff too. So again, now you're looking at the dark matter density as a function of radius. And this is from different state-of-the-art N-body plus hydrodynamic simulations. And we live way out here where most simulations kind of agree. And then each individual simulation track, so each color here, makes a prediction at large radii, and then you can extrapolate them into small radius with these dotted lines. And so that's kind of the zeroth order, like this is what we know from simulations. But there's something else plotted here. There's kind of like this increase, which is put in by hand. And what that is a potential dark matter spike. So the idea is that there is a supermassive black hole at the center of our galaxy, right? And so there's this adiabatic contraction model where as the black hole forms, it dominates the potential in the inner galaxy, right? That we should take for to be true. The dark matter particles are going to be dragged into the deepening potential well. And so as the supermassive black hole grows, if it grows slow enough, then basically you just do conservation of angular momentum. And what you find is that the dark matter density grows into a very large spike in the really inner region of the galaxy. And so this sort of prescription was first put forward by Gondola and Silk decades ago now. And so what these people did was this was actually a paper that was looking at heavy dark matter with Hess. And so these vertical lines here are roughly the Hess angular resolution that's relevant. And so they were kind of considering what happens if there is this dark matter spike in the inner galaxy. But you can see it's not totally clear what the shape of that spike should be like, as they thought. Okay, so I'm going to be looking at this profile as well, and I'm going to parameterize it kind of roughly in 3 regimes. So there is a regime in the very outer region, which, you know, for us, outer region is anywhere like around solar-ish, where there's one power law that describes it. There is a second power law that describes it in what I'm going to call the spike region, and then there's a flat core that's basically just where the density saturates. So in the very inner region, the dark matter density is really super high, which would lead to a high rate of annihilations, but a high rate of annihilations will then deplete the density. So it's basically just set by the time scale of how long this dark matter distribution sticks around. So the key features are, it looks like the initial uncontracted profile at large radius. The spike that's in between the large radius profile and the core is just set by the growth, the adiabatic growth of the spike from that core power law. And then there's the saturation that's set by the time scale, like the lifetime of the spike, basically the annihilation cross-section and the dark matter mass. Okay. So if we look at this thing in a little bit more detail, the different regions here I'm defining with these radii, the spike radius and the core radius. So the core radius is where it turns into a core moving to the center, and the spike is the one where the power law switches. The spike radius, to first order, and we'll address this later, but to first order, the spike radius is really just set by the gravitational sphere of influence of the black hole, which my astronomer friends will tell me is about 0.4 parsecs. The core radius is just set by that saturation density. So if we understand the saturation, or at least we can approximate it, then you can figure out what the core radius is and you know what the saturation density is. One thing that we're going to consider here that's a little bit more complicated than sort of the standard picture is that the annihilation cross-section, if you do the partial wave expansion, there's like a velocity independent term, and then there's a velocity suppressed term, right? And if the halo is virialized, then you can relate these velocities actually just to the radius. So it's inversely proportional to the radius. So now our annihilation cross-section is actually going to depend on the position in the halo where the annihilation is happening. Okay, and then as I said, the power law that determines the spike is actually just related to the power law from outside, or the power law from which it grew, and there's a simple expression assuming that it's just the adiabatic growth and these things are on circular orbits. So that's our beginning assumption. So here's what that picture looks like. So we've got the density as a function of radius. We live way out here. I'm picking some value of the cusp exponent, or gamma c, to be 1.0, which is basically NFW. And so this looks roughly NFW, and then you have this strong spike that grows, and you have the plateau. And so the things we're interested in are gamma c, which 1.0 is kind of a low standard value. From observations, this thing could go all the way up to 1.6. We really don't actually even know that. And then there's the spike profile, which here, the one that I'm demonstrating, is that from that adiabatic, like the standard adiabatic prescription. And then there's the saturation density. The other things that are going to be interesting are the spike radius and the core radius. Oh, and one more thing in this picture. So in order to construct this picture, you have to specify what the annihilation cross-section is and what the mass of the dark matter is. So this is for a very standard benchmark dark matter model, 100 GeV dark matter, mostly S-wave annihilation with a thermal cross-section. Okay, so what is not included here? There's a whole bunch of not included stuff, but let's focus on the stuff that's going to really affect this profile. So, and these are all enumerated in this Fields-Shapiro and Shelton paper from a couple of years ago, but I want to go into a little bit more detail on some of them. So one thing that is not included are gravitational interactions between the dark matter and the baryons. And the main way that this comes into play in the very inner part of the galaxy is through scattering of dark matter on stars. So basically, the stars are big and they're also moving, and so dark matter and stars interact gravitationally, and people call this heating of dark matter. And there are a couple different prescriptions for how that might happen. There could also be more invisible compact objects towards the galactic center than we know about. And by towards the galactic center, the relevant region here is within the inner 2 parsecs, basically. There was just a paper a couple months ago that showed there are a lot more of these objects than we initially thought. There could also be some dramatic dynamical changes that happened any time in the history of the formation of our galaxy that might have messed up what's going on at the galactic center, so things like mergers. Dark matter self-interactions might affect the profile. If the growth is not adiabatic, so this whole thing relies on the fact that the growth of the black hole is adiabatic, which is pretty slow. So if the black hole, the supermassive black hole at the galactic center either appeared suddenly, or if it started from a large seed, even if it started from a large seed and then the growth was adiabatic after that, if the seed was large enough, then you would expect a slightly different picture from what I presented before. Or if the black hole is off-center in the galaxy. All of these effects go in one direction, and that is to flatten the spike. So the one that I'm going to examine is the one where we kind of have a pretty good prescription for how to work with it, and that is the scattering of dark matter on stars. So we'll go into a little bit of detail on this one. Okay, so the idea here, again, is that stars near the black hole have much larger kinetic energies than the dark matter. And so they tend to heat up the dark matter, and that goes in the direction of flattening the spike, right? So you can, if we're thinking about the density in the spike, so we'll assume that there is some spike, right? If we think about the dark matter density in the spike, as time goes on, this thing is going to be flattened by this exponential, where tau here is the ratio of the lifetime of the spike to the characteristic timescale of heating by scattering on the stars. So what is that number? Well, we pretty much, I mean, the lifetime of the spike, let's just assume that it formed kind of as when our galaxy did. So we'll say this is like 10 gigayears, right? But the heating time is not really clear. It could be 1 gigayear, it could be a fraction of a gigayear, it could be a few gigayears. Anywhere in that range is totally realistic. In order to calculate the heating time, there are ways to calculate this, but it's a really complicated business. So it's one of the simplest parameterizations. Kind of gives you a feeling for how this works, but it's dependent on the mass of the black hole, obviously, the one-dimensional velocity dispersion cubed. M star is the typical stellar mass in the inner 2 parsecs of our galaxy, and then this N star is the number of stars in there. So that's like a million or 10 million or something like that. So you can get an estimate for the heating time, but again, we're talking like orders of magnitude uncertainty there. Another way of thinking about this, rather than thinking about it directly flattening the spike with time, is actually what it will do is it will change the spike radius, which, as you'll see, ends up dampening the spike as well. But this is a more modern way of parameterizing it. And these 2 parameterizations actually come from studies that Merritt and then later Merritt with other people did. But basically all of them, they did like the full calculation, the full numerical calculation, and then these are just parameterizations of the results that they found. Okay, so I'm going to call this thing a depleted spike if the spike radius changes with time according to this equation, and you can see that it is dependent on tau, which tells you about the heating time. So this is our depleted spike. And if I just take a spike where the spike radius does not change with time, I'm going to call that an idealized spike. So here's our picture, which I didn't tell you before, but was an idealized spike. So here's our initial spike radius that we're starting with. And now I'm going to allow it to deplete. And what happens to the spike is it becomes dampened, right? So you can see the spike is smaller, and the radii have both shifted. So the spike radius, notice that these markings are like every 2 orders of magnitude. So the spike radius has changed a lot. This is now a very small region near the galactic center. And the core radius has also changed. I'm plotting actually 2 different values of tau here. The one that I'm going to take as an example is tau equals 10, so that's the thick line, the thick dots. The thinner one is tau equals 4, just for reference. So even if you allow that heating time to be uncertain by quite a bit, you still get a pretty depleted spike.
It's still a lot shorter than the age of the galaxy. So billion, that's the dynamical time scale. So you would expect all this to have been already happened.
Right.
What happens if you change your mass to 10 GeV?
If we change the mass to 10 GeV,
the dynamical time scale will change. Everything gravitates at the same rate. So.
Right. It's not going to affect this picture too much, except for affecting the saturation density. But I'll show you the dependence on the mass a little bit later. Okay. So just to give you a feeling for this is the spike radius for different values of gamma c. So everything I showed you was for gamma c equals 1.0, which is the standard NFW value, basically. And so this shows you, in the idealized case, obviously the spike radius is not sensitive to gamma c or really anything else. It's just set at its initial value and then it stays there. For tau equals 10 or tau equals 4, the spike radius is smaller at 1.0, but if you go to a very large value of gamma c, the spike radius actually gets even smaller by a lot. Okay, so now there are dark matter annihilations in this spike. So obviously this is a big collection of dark matter. We can calculate the flux of dark matter annihilation products coming from annihilations in this spike. I'm going to be interested in the signature in gamma rays. And so basically all this stuff is normalization. It goes like the density, dark matter density squared, the annihilation cross-section to a particular final state, and then the spectrum of photons that you get from that final state. This flux, if you look at a large enough angle, you may actually see some of the outer portions, so like the cusp part of the profile, contributing to the diffuse, or contributing to the flux from the broader galactic center region. But this spike actually will contribute to the point source flux of the galactic center point source also. And so the Fermi-Lat galactic center point source that we're going to use is this particular one here, Sagittarius, which is identified with Sagittarius A star. And we're going to do this in a very hand-wavy way, which I'm going to warn you about now, but as you'll see, we're interested in like orders of magnitude changes between these different situations, so don't be too disturbed by my hand-waving. So we're going to just do the integrated flux. We're not using any spectral information. So integrated flux between 1 and 100 GeV. And I'm actually going to do this in a kind of agnostic way about what the dark matter is. So I don't want to have to care what my final state is of my dark matter annihilations. I'm just going to set this integrated spectrum to be 1. And then if we want to do a different dark matter final state, we can scale the flux with the integrated photon count. There's one thing that we have also hand-waved over, and that is that the spectrum actually is important. And so Fermi's point spread function really depends on the energy below 10 GeV. So we haven't included this. We've just taken like one standard opening angle, and we're going to pretend that that's good enough for our purposes, which it is. All right, so here are results for a depleted spike. So what you're looking at here, there are 6 panels. In each one, the x-axis is C0. I'm really sorry this is kind of fuzzy and not very bright. The x-axis here is a log scale of C0, so the S wave partial wave coefficient, and the y-axis is a log scale of C1. So a thermal annihilation cross-section roughly is 10 to the minus 26 cubic centimeters per second, which is like over here roughly in each plane. And in the top panels, the dark matter mass is 100 GeV, and the bottom panels, the dark matter mass is 200 GeV. And moving from left to right, we have gamma C of 1.0, so that's basically the NFW case, except we now have a depleted spike on top of it. And then we have gamma C of 1.3 and 1.5, which is getting towards the upper edge of what you could possibly imagine. The colors here indicate the flux in units of the Fermi flux from that galactic center point source. And so most of these values in the blue and white regions are well below 1. There's only one plane where the flux actually gets to the level of the flux from that galactic center point source, and that's in this upper right plane here. So for relatively light dark matter mass and for a very large gamma C. The solid, or the thick line here is the galactic center flux. Okay, so bottom line here is, if there's depletion, you're probably out of luck unless gamma C is pretty large, like as large as we can imagine, basically. This holds for really any dark matter model. We're talking like fluxes of 10 to the minus 4 in terms of the Fermi flux that's measured. So we're very far in most cases from what's measured. And also the velocity dependence is minimal. So we have included the velocity dependence, but you can see these contours only turn over if the coefficient C1 is much, much larger, like a few orders of magnitude larger than C0. So when we say velocity suppressed, as in C1 is the important coefficient, it really is velocity suppressed. So you usually don't have to worry about that. Okay, so we can look at the observational reach in a different way, and that is by fixing the annihilation cross-section to some sort of standard value, and then thinking about how the flux changes with dark matter mass for different values of gamma C. And so what this shows you is that, well, it goes like 1 over mass squared, which you would kind of expect. So as the mass gets larger, you really lose all hope of trying to detect things this way. And the other thing that's interesting here is that it's really only for these largest values of gamma C that you're getting to it. I think the other picture didn't really accurately, like, it didn't give you as good a sense as this does, that it's really just for gamma C huge that you're able to be able to hope to see something like this. Now, that's the depleted case. Which has actually not been studied that much. Something that has been studied a lot more is this idealized case. And in the idealized case, the conclusions are way, way different. So for the idealized case, it looks like if gamma C is bigger than like 1.2, 1.3, I should tell you that 10 to the 0 is 1. So that is the Fermi flux. If your contour is above that line, that means you're over-predicting the flux from that galactic center point source. So in the idealized case, it looks like many of these models are completely excluded already, which would make this a very powerful tool, right? But it's not really clear whether we're in this case or whether we're in this case. And if we are in this depleted spike case, am I actually giving you the right, like, have I done the heating time correctly? Yes. So one thing we can take away from this, though, is that there's about a factor of 200 difference in flux, depending on whether it's ideal or in our depleted case. 200 is a lot. I would like to give you an example. so we've applied this to completely general, like, let's say dark matter just has some coefficient C0 and some coefficient C1 that define the partial wave expansion of the annihilation cross-section, right? But it's, for me, as a particle physicist, I think this is more interesting if we actually put it in a context and see what we can say about a particular model. So one model that we're going to look at is just a singlet dark matter candidate coupled to standard model fermions via some mediators, which are going to be charged scalars. So this is what the interaction looks like. It's a T-channel exchange of some scalar mediator, and in a final state that's a fermion is a fermion here. Now this is a little bit of a tricky thing, because if you just wrote down this interaction, what you would find is that the S-wave annihilation is chirality suppressed. So the fermion masses are light, so you're not really going to have this in any amount. And the P-wave is velocity suppressed at freeze-out, which is actually enough to make it not a significant annihilation channel. So you would always end up with too much dark matter in these models. The way that you can rescue that, actually, is by having mixing of the scalar that couples to the left-handed fermions and the scalar that couple to the right-handed fermions. So here's the interaction in Lagrangian for what that looks like. The relevant thing here is that the scalar state that couples to the left-handed particles and the one that couples to the right-handed particles mix with some mixing angle alpha into their mass eigenstates, which we'll call 1 and 2, where 1 is lighter. So this is a pretty simple model. It has 4 mass parameters. There is the dark matter mass, the masses of the 2 new scalars that you need, and then whatever the standard model fermion is, or it could be a fermion, and it could be a beyond the standard model fermion in the final state. And then you need to specify your Yukawa couplings. Technically, you could have a CP violating phase, but the real thing that's interesting here is the scalar mixing angle. If you want to put this into a supersymmetric context, which you are welcome to, this is actually kind of like a corner of supersymmetric parameter space. So one thing, like I could consider singlet dark matter as a BNO. Fermions could be anything. I'm going to call them B quarks, and the charge scalars are going to be the B squarks that make this interaction happen. So if I want to do some benchmarking here, I'm going to take the Yukawas to be their values that are determined in supersymmetry. CP violating phase doesn't do a whole lot here, so I'm going to set it to 0. And then I'm going to pick some low masses for these guys. I'm going to decouple the heavier scalar, so I actually only need 1, as long as it technically has some heavier guy that it can mix with. Okay, if you would like to read more about these models, I think some of us were talking with me and Pat yesterday. We have a series of papers that I've worked on along with Pat Stengel, who is over there. So you're welcome to ask either of us about direct detection of these models, indirect detection of these models, LHC searches, you name it, we're happy to discuss it. So here's what you get in these cases. So this is for an idealized spike first, actually. And what we've done is we've just scanned through the parameter space in alpha, and it traces out this boomerang in the C0, C1 plane. You can plot that instead on a plot as a function of alpha. So the magenta contour here is C0, and you can see that for no mixing, it goes to 0, but then it reaches some maximum value at maximal mixing, basically, and C1 as well. And so you can follow this and trace out this boomerang in the plane. For the idealized spike, much of this boomerang actually lies in the excluded area. So that would tell us that this model is almost filled, except for, oh, it's a shame. This is actually grayed out. So what this tells you is that the model would have to be super fine-tuned. If I were to gray out the region of this plane that's excluded because the flux would exceed the galactic center point source flux, it would be everything except very near 0 and very near 0.5. If we do this in the case of a depleted spike, the whole thing evades detection. So not super surprising. But this is just an example that we're mapping this back onto particle physics properties, and you end up with a completely different conception of what your model of dark matter could look like depending on these astrophysical parameters. Okay, so here's the mini summary. Constraints vary dramatically with the properties of the spike. Is the spike depleted or idealized? We don't really know. There seems to be good evidence that it's depleted. If it's depleted, how much is it depleted? We also don't really know that. But it kind of comes down to this typical time scale for heating via scattering with the stars. So what I want to talk about now is just changing our perspective in the last couple minutes. And so the change in perspective is that I would like to ask the following question. If we understand something about dark matter, can we then use it to learn about what has happened at the Galactic Center? Okay, so this is a picture of the Fermi sky that many of you have seen before. And Carlos mentioned earlier this Galactic Center gamma ray excess. This is the the white circle here is the inner 12 degrees, which is kind of like the full area that you might consider, but most of the excess, of course, comes from the inner like degree or maybe 2 degrees. Early analyses of the galactic center gamma ray excess seem to indicate that dark matter was the best fitting explanation for these excess gamma rays. And so here's a plot from Cholis, Linden, and Hooper that shows 3 possible contributions to the gamma ray spectrum in the GeV range. And so the black data here are actually the data from Fermi with some massaging of them to make them into the thing that they want them to be. The red points are the globular cluster explanation, the blue points are the millisecond pulsar explanation. And so basically what they did was they tried to turn the knobs on those explanations to make them fit as best they could, and you see that they always had a problem at low energy. Now part of that depends on how they massage the data at low energy, but yeah, fair enough. So from this paper and several others, it was concluded that a 35 or 40 GeV dark matter particle annihilating to maybe dB bar or something like that was the best explanation for the excess of photons coming from the galactic center.
What if you add globular clusters and millisecond pulsars? Doesn't that fit pretty well?
Huh? Well, yeah, so this was old, there's new. So back in 2014, everyone who looked at it really said that the energy spectrum, morphology, and annihilation rate were all consistent with thermal with dark matter with an NFW-like profile. And even the Fermi collaboration said that peaked profiles with long tails yield the most significant improvements in data model agreement. Now, that was old. That was a few years ago. This year, there is a new analysis that is pretty definitive, I think. And so this was by the Fermi collaboration, and I think it was in January, actually, it's pretty early. And basically, what they find is that when you include more carefully millisecond pulsars and you do the background subtraction, point source subtraction differently, what you find is that the spectrum and morphology of the excess are not obviously consistent with dark matter annihilation. And even if there is dark matter annihilation, it does suggest an underlying astrophysical component, which could be all of it. And furthermore, I think maybe the most damning thing here is that this is also consistent with the presence of a similar fractional excess along the galactic plane where no dark matter signal is expected. I would say this is probably a nail in the coffin. That's what I would say. So I think we can put that as a pass then. But I think it's still instructive to take this example of, hey, if we had a dark matter candidate, what can we learn about the galactic center? And so I'm going to take that model. The model that I'm going to use comes from this different paper, but it's Annihilations to dB bar with a 50 GeV length with some specific, roughly thermal annihilation cross-section. So what you're looking at here are the constraints in the gamma C, so that's like the cusp exponent, gamma spike plane. So that adiabatic relationship for the spike exponent to the core exponent is actually given by this dashed line. It yields leads to pretty large values of gamma spike. But we allow gamma spike free here. So the very thick line is the observational limit. So everything to the right of this is excluded. Again, you can move these things around a little bit. We're interested in like order of magnitude trends here. But this tends to disfavor large gamma C. Okay, so maybe you can say something about it. I think one of the most interesting things here, though, is that the contours are basically vertical. What that means is it's independent of the spike exponent. So what you're seeing here is not actually the spike at all. What you're seeing is just the very inner part of the regular old cusp. Again, the heating timescale is really a critical thing here. If you want to understand the limits on anything related to the very center of the galaxy, you have to know, well, if that scattering on stars mechanism is the primary one, and then what the heating timescale is. Okay, so here is my very brief summary. Is or was there a spike? Maybe, I might say probably. Is it depleted? And if it's depleted, how much is it depleted? And we really, at this point, cannot tell at all. But if it's depleted, then you get pretty strong constraints on dark matter models. If it's not depleted, you get pretty strong constraints on dark matter models and tension with the dark matter explanation of the galactic center excess. So that tells you that this is a very strong probe of what's going on in the spike if we do have a dark matter model. If the spike is depleted, though, first of all, it may not be. There's like, in most of the parameter space, it's not really a spike at all anymore. And it really doesn't help you say much about dark matter in the inner region. So the bottom line is that modeling of the astrophysics near the galactic center is complicated, but it's really, really important in terms of using these tools. And I think in the future, hopefully we will know something about dark matter, and then we can probably use it to say at least broad things about what the dark matter distribution at the very center of the galaxy looks like. Thank you.